All right, so we are picking up. We are on the bottom of page 71. And I already did a little bit of writing, so some of it I'm going to have to put my sticky note over because I got cut off on the video. So yeah, just ignore what's under the sticky note. Here we go. All right, so let's go to this problem. So the difference between this problem and the first problem that we did is here our population was growing. In our next example, you're going to see that it's going to be decreasing. And to show decreasing, we're going to have to do a little modification with this formula. Not much, but pretty simple. So it just says throughout the 20th century, the population of giant pandas was decreasing at a continuously compounding annual rate of 2.5%, which I've already turned into its decimal, due to poaching and habitat loss. So if there were 10,000 pandas in the world in 1900, what was the population in 1980? So for here, when I do this, we're going to put, the P of T. And T is just, again, our time in years. P is the number of pandas. So there were 10,000, and now we want to know what's the population in 1980. So this is going to be our beginning amount, and we're going to be solving for P. So our population of pandas based on time. So my beginning amount is 10,000. It did say compounding continuously, so I'll put that E in there. And then for my R and T, I do want to put the 0.025 and T for time. But what's going to happen is if I leave this as 0.025, it's going to assume that the population is growing. So to show it being decay, what I have to do is take a negative and put it right in front of that rate so it knows it's going down. Because remember, what a negative exponent does is it's taking this and it's moving it to the denominator. So essentially what the calculator is about to read is this. It's dropping E, this 2.7 number, into the denominator. And we did discuss when this value is bigger than 1, then it's growing. And when it's under 1, it's decreasing. And 1 divided by, that's about 3, is 1/3. So that's in between 0 and 1. So by putting the negative, I will be showing that decrease. Now, we don't have to do this. You can just leave it as the negative. So what we want to do, if there were 10,000 pandas in the world in 1900, what was the population in 1980? So what I'm going to do is just take my equation and from 1900 to 1980, that's 80 years that has passed. So there's a little time sign. And now I can just go to the calculator, type this in. So wrong screen. So I can just type in, sorry, I'm trying to get it so there's not a glare here, 10,000, hit that E button with second ln, negative 0.025 times 80. And remember, be sure to type the negative button, not a subtraction button. And so here we go. So when we are done, we're going to see that our population is now down to 1,353 pandas. So it's really dropped. So the amount of pandas will be 1,353 pandas. I'm going to drop the decimal because we will have a partial panda. All right, the last one, and I'm going to go until this bell rings, so we'll see how far we get through all of this. The next thing we're going to talk about is half-life, and maybe in chemistry you've heard about half-life and radioactive isotopes. So when in nuclear power plants, they are powered with a particular radioactive isotope called uranium-235. And what they do is this nuclear active waste, this radioactive isotope, decays, and that's what gives the power off. That's what gives power. But it's a very radioactive, which is not safe, so they do need to contain it. And one reason why people like this so much is that it lasts forever. And so what we're going to talk about is half-life. Half-life is the amount of time that it takes for half of the quantity to decay. And so when it reaches its half-life, it's now stable. But before that, it's unstable. So again, that's why this radioactive isotope needs to be contained, because it's unstable. So this is all kind of going back to your chemistry class, and here we go. So let's take a look at our first example. Uranium-235, the radioactive isotope used in nuclear power plants, decays at a continuously compounding rate of this much percent. This is the percent. This isn't even the decimal. So when I do turn this into the decimal, this is a very, very small decimal. I mean, this isn't even 1%. This is 9/100 of a percent. It's so small. It decays very slowly. So what we're going to do is we have to figure out, if you started with this many grams of this type of uranium, what is its half-life? And half-life just means it has half the amount that it started with. So that means we're going to go till we hit 50 grams. So what is the half-life? So when they say what is the half-life, I know the half-life is 50. What I really want to know is how long will it take me to get to 50? So if we kind of follow our PERT formula, we're going to use, instead of Y, we're going to put the radioactive amount based on time, and our beginning amount is 100, and then E to our decimal point, here we go, 0.00985, and then our goal is to figure out how long it will take. And so our half-life, again, is, we're going to replace this with 50, because 100 is 50. So just writing this down. And we still don't know at this point how to solve for an exponent. So what we're going to do is use our graphing calculator. So I'm going to go to the y equals button. I'm putting this into y1 and this into y2. So you'll see this in just a moment. And again, when I start this, I always just start with zoom 6. My little wheel is spinning. It's not fitting in my standard window, so once that wheel is done spinning, then I'll do zoom 0 for zoom fit. And so the first thing you're going to see is the 50 going across right there. And here's this one. And I'm going to pause. I'm going to get the window adjusted. Alright, so little mistake here. I forgot, I wasn't paying attention, that this is decaying. So I will need to make sure that I put a negative here. So I've already adjusted that in my graphing calculator, and I've done zoom fit, and here is the first line, there's that 50, and here's the exponential curve, this is the other side. So I just need to go more to the right and down. So going more to the right, I'm going to try, gosh, I don't even know. It's going to take a long time. So let's put 500 in. And then I actually want to go a little bit lower. So I'm just going to put 0, and let's see what happens. Oh, there we go. So how long is it going to take to get from 100 to 50? Now realize 100 milligrams is, or 100 grams, that's still not a lot. In a nuclear power plant, there would be a lot more, and it would take a lot longer for it to reach its half-life when it's decaying at such a slow rate. But now that I've seen where they meet, second trace, choose option 5 for intersect. And then I'm just going to hit enter 3 times. And then I will get that it is 70.37. So the time is 70.37. And again, that just means, sorry, my watch is telling me I need to stop this video, that it's 70 years. And if you want to see how much 0.37 is, 0.37 as far as years go, 0.5 is a half a year. If you want to know exactly how many months that is, you can do 0.37 out of 12 months times 12. And so it's a little over 4 months. So 70 years and 4 months. Okay? And that's it. I think that's the only one we're going to do as far as half-life goes. And those are your notes for 5.4.